Hello there, math fans. This is Dr. Andy Loveless. Going to continue our introduction to curves in 3D, but here I'd like to just motivate one of the intersection questions that I think should be interesting to you, which is the intersection of curves and surfaces. I think this gives, for those of you that feel funny about parametric curves, I hope to show you that this is something that is very interesting. And in the next video, I'll show you how to solve. And these are some of the easiest to solve. But I just was thinking about some things that you might have encountered. For example, if you want to know how do you measure the distance of a home run. Now that's sort of a parabola. Now if you're going to deal with air resistance, you'll have to adjust. But I found a little visual of that. That's an intersection. The question is, when would that curve intersect the ground if it was extended out? I found a picture of like a path of a tennis ball. I'm really interested in that. How does it intersect? What if you allow, it to curve? Maybe more interesting to some would be, how do you design your path so that when you send your module out, you want it to land on the moon? That's being more exotic. Curves are all around you. And so I just was thinking about this. So the other day I was walking through the cherry blossoms, if I could say it, and all these students started to say they wanted to throw water balloons at me because they were so frustrated with the courses I've taught over the years and really don't like me very much. So they set up here to throw these water balloons at me. So here we go. This one was like, I think I can hit him in the face with this red water balloon. That's a 3D motion. My head is this weird ellipsoid you're trying to intersect with. So here you go. I think he threw it. And it hit me. Aww. Okay, so intersections of curves are interesting. Here's my model I made. What if you were allowed to change the angle and the initial velocity and you wanted to hit the person? So the reason I can do stuff like this is because I've taken 3D calculus. Here's me adjusting the angle. This is my big head, ellipse head. I want to hit it. If you actually wanted to solve it, so you can use this, a grapher like I'm doing to solve something like this. But if you actually wanted to solve it and think about the possible angles that would hit it, you would need to know a little bit of calculus, and then you could actually throw your water balloon. Ouch, went right through me. Or for you baseball fans, you could step out a little further and say, what if I'm doing the same question, but this time I'm going to be hitting a baseball from home plate? I started to set that up to make it more realistic, and then I thought I'll just say it. So imagine you're trying to hit a home run. You got a 300-foot fence or more or something, whatever you set it up as, you want to hit over that fence. How do you do that? What's your initial velocity? What can happen? How do people measure such a thing? The moment you start to ask about intersections, it's a curve intersecting in 3D with some surface. We're going to tweak the initial velocity. We're going to send the thing going. Let me add a little bit to this. I need to increase my initial angle. I need to increase my exit velo. They always talk about in baseball. There we go. We've increased our exit velo. We work on the angle a little bit. Those are intersection of curve questions. Just grabbing ones that some of us may know or have encountered. And then you may say, no. I don't want to just hit a home run. I want to hit to the upper deck. Well, the upper deck might be some sort of plane. How am I going to hit to the upper deck? Well, I might have to increase my angle, increase that exit velo. So if you wanted to study, the point is, you may not be interested in that question. You don't know what baseball is. But if you wanted to study such a thing, these are some of the tools you could use to figure it out. Okay? The more you work in 3D. The questions in 3D are harder to figure out, like what the standard question is. But intersection is really easy to find if you can find the equations. That's the hard part. The intersection part shouldn't scare you. I gave an exam a few years ago where students were like, "You will ask lots of intersection questions, you jerk. That's why we want to throw water balloons at you." And I was like, the intersection part's not hard. It's the getting the equations to match data. Okay, so then I made this model. Like I said, I was trying to come up with examples. So here's the Earth and the Moon. This is not accurate in any way, but we're going to send the moon going around, and we would like to send our rocket to follow it. Boy, that seems like a hard question to me. So it'd be nice if ahead of time we could do a little bit of math and predict where it's going to go. I'm not going to claim any of what I'm about to do is accurate, but in order for me to graph this, I had to think a little bit about it. There's a spiraling out thing. Let's let it go. I'm hoping when my object actually gets out there, here's my satellite. I sent it firing. I want it to get next to the moon. This is not an accurate model at all, but it'd be nice to know that it gets there. All right. So that's just a little bit of motivation. In the next video, I'll talk about solving. You can do more exotic things, but I wanted to focus on practical first. So here's an exotic curve that actually doesn't take very much to give, just a spiraling thing. It's got some object that's going to spiral around on it. And my intentions are to show you where that would intersect a sphere and show you that I can solve that problem in a matter of moments. It's not a hard problem because the equations go together nicely. So yes, the visual will be kind of weird, but the solving is easy. These are the easy solving questions. Okay, so follow up, watch my next video if you want to see how you solve such a thing, provided you have the equations. If you have the equations, combining them and solving is quick. Okay, so that's for the next video.